Okay, so this one is going to be a little bit more tricky, but let's go through how we're going to construct and prove our construction of what's known as a perpendicular bisector. So here I have the symbol for perpendicular, so it means perpendicular bisector of some segment. So what is the perpendicular bisector? Well, it's exactly what it says it is. It's the bisector. So for example, this line right here is a bisector, let's say, because you have that this side is congruent to this side. But it is not perpendicular. So it's not the perpendicular bisector, and every segment only has one perpendicular bisector. So this line right here, what I just drew, is a bisector of AB, but it is not perpendicular, therefore it's not the perpendicular bisector. Likewise, this line here is also a bisector of AB, but again, it's not perpendicular to AB. And to put it in contrast even further, so I have those lines were bisectors. This line right here, what's going on? This line, what did I do? Oh, that's why. This line right here is indeed perpendicular. It forms a right angle, but it's not a bisector, right? This line right here is perpendicular, but it is not a bisector. This side does not equal the other side, and the same thing for the other one that I just drew. So the line that satisfies both of these conditions is the perpendicular bisector, the line that goes like this. Because let's check now. Is this line perpendicular? Yes. And is it a bisector? Yes. This one is congruent to this one. So then therefore it is the perpendicular bisector, and there's only one. And we need to now be able to, if we're given some segment, construct the perpendicular bisector. So how do we do that? We do that in exactly the same way we constructed an equilateral triangle. So the first thing I do is I go to point A, and I open up all the way to point B. And from A, with the center as A, I draw this first circle. Okay, and again, my circle will not be perfect. I'm trying to make it perfect, but I draw this first circle. Okay, and you don't need to draw the full circle. You could draw a semicircle like I am right here. But it'll be much easier for you. It's easier for you than me to draw the full circle. But okay, now after you do that, you go to point B and you open it up to A again. You leave it at, as it's opened up, and you draw another circle. And you take note of where it is that these two circles intersect. So let's call this point C and this point C prime. Okay, the claim is that the line through C and C prime is the perpendicular bisector of AB. Why? Let's prove this statement together. So to do this, let's draw in these equilateral triangles that we also simultaneously created. So let's say we have this. And what is it that we want to do? We want to prove that this line CC prime, right? This is the line CC prime is perpendicular to AB. And, right, what else do we want to prove? That this point D, where it intersects, we also want to prove that AD is congruent to BD, right? That would guarantee that this line, and I should say line, right, CC prime, that's one way I could denote the line by putting the 2 points and then the arrows at the end, okay, is perpendicular to AB. I need to prove that. So I need to prove this statement, and I need to prove that this is congruent to this. So let's go about doing that, okay? So the first thing I'm going to state is I'm going to state that, let's see, what do we have here? I'm going to state that triangle CAC prime is congruent to triangle CBC prime. Why is that the case? So I say that's true from side. Okay, so this side is the same as this one. This side is the same as the original, but it's also the same as the other one. And then this side, they share. This is segment C, C prime. So these two triangles are congruent. That means all their corresponding parts are congruent. So that means that this angle will be congruent to this angle. Okay, after I show that they're congruent. Now the next thing that I'd have is that this here, we proved this triangle, ABC, is an equilateral triangle, which means that all of its angles are congruent, which means that this angle is the same as this one. So these two angles are congruent, right? This triangle is equilateral. ABC is equilateral. So and therefore all of its angles are congruent. So this angle is congruent to this one. Now I have angle, side, angle. And these two triangles, let's go through the triangles that I'm referring to now. Let's make it a different color. Let's make it green. This triangle, right? If we look at this triangle right here is congruent to this triangle right here. Okay, because of angle, side, angle, right? Angle, side, angle. And once I have that these two triangles are congruent, I'm pretty much done. I could state this one fairly quickly, because then that means that this angle is the same as this one. And we can see that they form that straight line AB, the segment AB. So then that forces both of these to being 90, which shows this statement. And then we know by CP/CTC that this segment then will be congruent to this segment. And I've shown this part here. And then that shows that this really is, this C prime line is perpendicular bisector of AB. Because I showed this one and I showed this one, which are the two conditions for it being a perpendicular bisector. Let's go back. Let's write it out a little bit more clearly. Let's write it out in the statements and reasons. And we're going to redo the argument again. We just did theory. You should have followed along. If not, see if you can follow along now. And then if not, watch again. So let's see. How far do I want to go back? Okay, so let's write out the statements and reasons. And it is rather long because we have to prove a bunch of triangles congruent. We got to use CP/CTC a few times. But okay. So I say that AC, this length, is the same as AC prime. Why? Well, let's see. A is the center of this circle here. And C prime are both on the edge of that, right? So AC and AC prime are both radii. So I'm going to claim that and then actually I'm going to claim that these two are the same, right? They're both, this length and this length is the same. It's an equilateral triangle. This length, that's what I really want. Because I want to show that this triangle, this triangle here, this triangle here is the same as this one on the other side of it. And I'm just going to say that AC is congruent to BC by my construction, right? They're both AB away, and they're both part of that equilateral triangle. We proved that this is an equilateral triangle in our last one, so we'll just say that these four side lengths are all the same. So I'm going to say it how I want it. So I'm going to say AC is congruent to BC. I'm going to say that AC prime is congruent to BC prime. And I'm just going to say by construction. It's really because we know that these are equilateral triangles that I could state this fact. And then I'm going to say the redundant one. I'm going to say that this C prime segment, C prime segment is congruent to itself by reflexive. And what that allows for me to say is that this triangle, so these two triangles are now congruent. This one, right, and this one. And let's state it in the right way. So triangle CAC prime, CAC AC prime is congruent to CBC prime. And that's side, side, side. And now I want to use the fact of CPCTC to say, let's call this angle 1 over here, right? And then this angle 2 right there. So now I could use CPCTC, right? Both of these two angles must be congruent. So angle 1 is congruent to angle 2, and that's because of CPCTC. Now that I have that, okay, I need to use the fact that this triangle is an equilateral triangle to say something else. So this triangle, this purple triangle that I'm highlighting here, right, is equilateral. And that's something that we did in the proof of our construction of equilateral, right? These side lengths all are side length AB, right? I opened up my compass, I drew a circle over here that's, of length AB, and this segment is clearly the same as this segment length. So this purple triangle is equilateral. So I'm just going to state 5. Triangle ABC is equilateral. And I'm going to say by construction again. And you could prove, or we could say by the construction of an equilateral triangle, what we did before, right? We proved that this triangle is equilateral. Now, in an equilateral triangle, all of its angles are congruent. So then that means that this angle is congruent to this angle. Okay, and I'm just highlighting something else, but this angle then is the same as this angle, right? So I'm going to state that. I'm going to say, let's call this angle 3 and this angle 4. And I'm going to say angle 3 is congruent to angle 4. And that's because all the angles in an equilateral triangle are congruent. So yeah, let's just write it. All angles in equilateral triangle are congruent. 7. After that, now if you look at this, right, I know that this is congruent to this. Or let's do a different color again. Let's say I have this line is the same as this line. I mean, again, just by our construction, it's an equilateral triangle, a whole bunch of ways. So this segment is the same as this one, right? That's saying AB is congruent to BC. AB is congruent to BC. I already have that. And I have that 1 is congruent to 2. So let's look at the two triangles that I'm proving congruent now. And let's use a color that's going to contrast. Here we go. So let's look at the triangles. This triangle, right, I'm going to prove congruent to this triangle. So look at the two white triangles if we can. This angle is 1. This angle is angle 2. This angle is angle 1, and they're congruent. This angle is angle 3, and this angle is angle 4, and they're congruent. This side is congruent to itself, and I need to state that because I haven't yet. CD is congruent to itself, and that's reflexive. And now I'm in a position to state what I want. Oh, no, I don't even need the fact that that's reflexive. I apologize. Yikes. Okay, so I cross it out, so I don't need that. 7. I already have it because this I have that these two sides are congruent. And then I have angle, this side, and then angle 2 and angle 1 are congruent. So I have that BDC is the same as ADC by angle side angle. So triangle ADC is congruent to triangle BDC by angle side angle. 8. And I'll state the two things using the same reason, CPCTC, real quick, so I could end it with my 9th last step, which will be the conclusion, that these two things are true, okay? This forces, let's call this angle 5 right here, this corner angle, 6. This forces 5 and 6 to be congruent. And then if we make a quick argument, 5 and 6 both sum to 180. So then that forces them both to being 90. So I'm going to state 5 is congruent to 6, which forces measure of 5 to equal 90. Okay, and that's because of CPCTC and just doing some algebra. That measure of 5 is 90 degrees, which means that this is true. They're perpendicular, right? This line and AB are perpendicular because this is a 90-degree angle. Now, also with 8, I'm going to say that AD is congruent to DB by CPCTC. Okay, because of CPCTC. Look, this triangle is the same as the other one on the other side, so then therefore all their side lengths are congruent. That forces that D is the midpoint, or that C, the line C prime, is a bisector of AB. And now you could just state the conclusion that C prime is perpendicular bisector of AB, because it satisfied the conditions for being a perpendicular bisector. This segment I just showed in the last statement. I just said this segment is congruent to this segment. That means that CC prime is a bisector. And then in this one, right, I showed that this angle is 90 degrees. That shows that it's perpendicular. So the reason for 9 is definition of perpendicular bisector. And you're done now. The key here is, look, this, however organized, not organized, the key is to see the theory.